Yeah, so I'm going to be speaking about algorithms for sparse instances of the max-sat problem. This is based on joint work with Rahul and Chen. So first define the problem. So the max-sat problem, and then the special case of it, which is the max-k-sat problem. You're given as input a CNF or a k-CNF on n variables. And you're asking for the maximum number of satisfiable clauses in the formula. Of course, you could also have a decision version of this where you're given an additional parameter, say r, and you're asked if there are at least r clauses that are satisfiable. But these two problems are polynomial time equivalent. So we'll be considering this version through the talk. And just some general notation through the talk: n will be the number of variables in a formula, and m will be the number of clauses, and k will be the clause width. And we'll be interested in this parameter c, which is a clause density. So we'll be interested in cases where the formula is sparse, which means that c is a constant. So that's just a number of clauses divided by a number of variables. So the question is, what are the best? So we want to solve this problem exactly. I mean, of course, there are good approximate solutions, but we want exact solutions, and we want to know what kind of running time we can achieve for exact solutions to this problem. So generally speaking, this definition of savings of an algorithm will be useful to kind of present our results. So for a problem, it has savings s, where s is some function of m and n. If there's an algorithm running in time 2 to the n minus s times poly of m. So s is intuitively the amount of savings over brute force search. So in general, n is some parameter that kind of represents the size of the search space. In this case, the size of the search space is just the number of possible assignments, which is 2 to the n. So that's what you're trying to save over. And you'll have some additional factor, which is polynomial in the instance size, which we'll kind of be suppressing mostly through the talk. We won't be that interested in it. So we'll be interested in achieving savings as large as possible for this problem. So it's not hard to see that under the strong exponential time hypothesis, which says that, which for example implies that CNF sat doesn't have savings omega n. That would also imply that max sat does not have savings omega n, because max sat is a harder problem than CNF sat. So we can't really hope for that in general. So if we want savings that's linear, then we'll somehow need to restrict the instances that we consider in some way. So there are a couple of natural restrictions to consider. One is to actually restrict the clause width. So that's the max k-sat problem. There's a theorem of Williams that max 2 sat is in time 2 to the omega n over 3, where omega is an exponent of matrix multiplication. In this particular case, it's, I think, more intuitive and natural to present the actual exponent rather than the savings, because it's related to the exponent of matrix multiplication. But it's open how to get linear savings for any k that's bigger than 2. So this is one of the major open questions in exact algorithms. So there's a very interesting restriction to get algorithms, exact algorithms for max k-sat for k bigger than 2, but we don't know how to do that in general with linear savings. So we'll be interested in this talk instead in the other restriction, which is the restriction on the clause density. So we're looking at clause density that's linear, and we want savings in terms of that. And that's what we'll be achieving here. So there were such savings known before, which are linear when the clause density is linear. It's just that our results are improve on those in terms of parameters. Theorem. So let's say there are 3 parts to this theorem. So the first part, savings omega of n over c. So there's a polynomial space algorithm for which we can get savings omega of n over c. And if you relax the space constraint and you allow exponential space, then there's an algorithm that has savings n over square root c. And in general, if you have savings that's linear for k-sat or for r-sat, then we get improved savings for CNF sat with sparsity c. So savings omega of delta n for k-sat. Okay, so delta is kind of some kind of linear savings for k-sat, but this delta might, of course, depend on k. So the omega here is a factor which doesn't depend on k. And I'm trying to capture the savings that you get for max-sat as a function of that delta and c and k. Yeah. So, well, this result B here follows from C by setting k equals 2 because there's linear savings for max 2 sat. So result C is essentially a reduction in general from max sat instances with Cn clauses to k sat instances. And the larger if you get linear savings for larger k, you get better and better savings for max sat with Cn clauses. If there's anything that's unclear at any point, feel free to interrupt. Okay, so those are our results. And now I'm going to talk about the general kind of algorithmic technique we use and the analysis technique, which is maybe more interesting than the algorithmic technique. So it's a very well-studied, well, perhaps the most well-studied algorithmic technique, which is branching. So let me just kind of present a certain kind of view of branching algorithms. So suppose you want to design a branching algorithm for CNFs, let's say for k-sat, then in some sense you want to explore the tree of assignments. So let me represent a branching tree in this way. So you have and so on, and then you have the leaves. So you have a tree, and the nodes of this tree are labeled with the formula at which you're calling the algorithm. So initially you're calling the algorithm the formula phi. And you somehow choose a variable to branch on. So you set the variable to 0 and explore the space of assignments with the variable set to 0. And then if you don't find a satisfying assignment there, you set the variable to 1 and explore the space of those assignments. And you do this recursively until somehow this formula phi simplifies to the extent that you can solve it in some easy way. Right? And we'll describe how the simplification works shortly. So the variables here just represent the variables you're branching on at each stage. And what would simple mean to us? Well, simple will mean that the formula actually simplifies to a constant that is either identically 0 or identically 1, because then, of course, you know whether the formula is satisfiable or not. So this is kind of one version of a branching paradigm for satisfiability. So when you design a branching algorithm, there are kind of two aspects to it. One is actually designing the branching heuristic or the branching rule. How do you choose variables at each stage to set? And the second is how do you simplify the formula, right? So we're going to be considering like very straightforward kind of simplification rules. So simplification rules. So there are various complex branching heuristics and simplification rules that are used in literature, but in this talk we'll be concerned with very straightforward ones. So the first one is if a literal in C, in clause C, is set to 1, delete C. Right? So yeah, that's obvious. And if it's set to 0, then you just delete the literal. And if a clause becomes empty, set phi to 0. So if a clause becomes empty, that means it's unsatisfiable, and so you set the whole formula to 0 in that case. So yeah, I mean, so these simplification rules are very straightforward, and it's unclear that you can achieve anything interesting using these simplification rules and a branching heuristic. But in fact, there's a very natural algorithm which achieves asymptotically the best savings we know for k-sat, just using these simplification rules and a very naive branching heuristic, which is just choose a variable at random at each stage and set it at random, right? So that's kind of a very kind of simple algorithm. At each stage for the formula, you pick a variable at random, set it at random, either to 0 or 1, and then explore the space recursively after simplifying the formula in this way. This actually gives you savings omega of n over k for k-sat, which is the best known savings we know for k-sat up to a constant factor. So it's kind of a folklore result. So I should say that if you're interested in the exact constant here, then there are better algorithms such as the Patury-Pudlak-Sachs-Zane algorithm, which gets you actually a constant bigger than 1 here. But if you're not interested in the constant, then this is a fairly simple algorithm which has very fairly simple branching algorithm which has this performance. And the proof of it actually goes by a star switching lemma. So it's kind of different from the analysis of branching algorithms for graph theoretic branching algorithms in the sense that it's not so much local as global. So usually when you're trying to analyze a branching algorithm, you set up some recurrence, some fixed term recurrence, and then you solve the recurrence to get an estimate on the number of leaves of the tree. But for KSAT, it's not so clear how to do this, and instead you have some kind of a global analysis which bounds the size of the tree in a different way using certain concentration bounds. And I'm not sure I have time to talk about it for KSAT, but I'll be talking about something similar for MaxSat, and that should give you the general idea. But I just want to present the branching paradigm for KSAT, and want to explore the possibility of extending this to MaxSat. So this is something that solves KSAT, but how do you extend it to MaxSat? Well, I mean, the main issue is that for MaxSat, this notion of a leaf doesn't make much sense anymore, because, well, if the leaf is a 1, then of course the formula is satisfiable, all clauses are satisfiable. But if it's a 0, then you're not getting any information. I mean, that's what you want to find out, how many clauses you can satisfy. So just the fact that the formula is unsatisfiable doesn't give you information. So we need to have a different notion of a leaf somehow. That also means that you need a different notion of simplification rule, because this simplification rule is not going to be helpful to us. It's kind of removing important information. So we're just going to modify this last simplification rule 3 in kind of a minor way, and let's call it 3 prime. And we'll just say, if C becomes empty, we just delete C. And the point is, and now we also change our notion of a leaf, right? So the notion of a leaf earlier was that the function became a constant, either a 0 or a 1. But now the notion of a leaf will be that you have a 1 CNF here. So you have formulas which are 1 CNFs. Let's say psi 1, psi 2, psi 3, psi 4, and psi I is 1 CNF. So that'll be a leaf. The point is that once you get to a 1 CNF, solving MaxSat is easy in polynomial time. So there's 2 things. The first is that with this notion of a leaf, you can solve MaxSat in polynomial time for the leaf. But also you're preserving information all along the tree as you're branching. Because, when you're deleting a C for which the literal is set to 1, you keep track of the fact that that clause is satisfied. And similarly, when a clause gets deleted because all the literals are false, you keep track of the fact that it's unsatisfied. And thereby, at any node in the tree, you know how many clauses have been satisfied so far and how many have been falsified. So that at these leaves, you have a certain number of clauses, one clauses. And for the rest of the clauses, you know whether they're satisfied or falsified, right? So basically, solving MaxSat for each leaf is going to give you the solution for the MaxSat for the original instance phi. So this is kind of this is how branching works for MaxSat. But with this simplification rule, a lot of the advantage we were getting in this case to get savings omega n over k was from using this simplification rule, that the function became a 0 when C became empty. Because that was going to happen with significant probability, and that's going to give us our advantage. So the fact that we've kind of relaxed the simplification rule so much is unclear if they will get anything at all now. And this is somehow the insight of this paper of Sakai, Seto, and Tamaki, which is the predecessor of our paper, which we build on. And they show how to analyze the case when you use this simplification rule. So this is the result. From the SAT conference last year. So the branching rule is going to change slightly, and in fact it's going to be good in a way, because the algorithm will now be deterministic rather than randomized. So earlier the branching was random. At each node, you just picked a variable at random to branch on. And now it's going to be greedy. You're just going to pick a variable which occurs the maximum number of times in your formula and branch on that. So that's going to be the branching heuristic. Again, a very simple branching heuristic, and also one that can implement deterministically. And with that branching heuristic and this kind of modified simplification rules, they get savings that's n over k squared c squared for max k sat. So I should say it's max k sat here. Max k sat with Cn clauses. Okay, so that's the result. So let me give some idea now of the analysis and of kind of the main lemma. So there's kind of a global analysis which I perform on the tree, on the recursion tree, in order to bound the number of leaves in it. So let me just give you an idea of how that works. So somehow, kind of a key lemma, a main lemma here, is this kind of like concentration result. So there exists a P and P prime such that. So this, yeah, this P and P prime less than 1. So look at depth kind of p times n of the recursion tree, right? So you have some parameter p, and you look at all the nodes at depth p times n. So there's a set of nodes here. You look at these nodes, and you look at the formulas that occur these nodes, right? The formulas that correspond to recursive calls at those nodes. So let's say phi I1. So you want that with high probability that some event happens here, and that the high probability event is that there's going to be very few nodes which have lots of clauses that aren't one clauses, right? And you want this event to happen with very high probability. So now phi I, so probability over, I guess, the choice of R from nodes of the tree. So R is in a level Pn. That phi R and phi I R has So this is kind of like the lemma that kind of underlies their analysis. So at some fixed p less than 1, if you look at all the nodes in the recursion tree at that depth, and if you look at the formulas corresponding to those nodes, then the probability that's a randomly chosen formula at that level has more than this many clauses with width larger than 1 is exponentially small. And this is kind of a key element. You need this probability to be exponentially small. So let me say why this is good. So why does this give us an algorithm with linear savings? And then maybe I'll just give you some very, very rough intuition on why something like this holds. So the reason that this gives us kind of linear savings is that, okay, so you can look at two kinds of nodes, right? The good nodes, so the nodes that satisfy the complement of this event, and the bad nodes, the nodes for which this is true. Well, the bad nodes have exponentially small probability, so there's going to be only 2 to the minus omega p prime n fraction of them. And if you just do brute force search on all such nodes, you're not going to spend time more than 2 to the n minus p prime times n. So the savings corresponding to these bad nodes is going to be omega of p prime times n. And as for the good nodes, what you can do is you can just look at these clauses that are bad, these clauses that have width bigger than 1, and each of these clauses is going to be a size at most k. So you can just look at all literals in these clauses and branch on all of them. But that's not going to be too expensive because you'll only branch on 1 minus p prime times n variables. So the total number of variables that you would have branched on, well, p times n to start off with, and then 1 minus p prime times n here. So there'll still be p prime times n variables left, which essentially you're saving. I mean, that's the savings of the algorithm. So in either case, you're saving p prime times n. And just by setting p prime equals 1 over c squared, k squared, and setting p appropriately, you get the result that Sakai, Seto, and Tamaki have. And as for some intuition why this kind of like strong concentration result holds, well, it's because somehow when you look at the CNF as a formula, it kind of shrinks quite significantly when you set variables in greedily. So when you set variables greedily to 0 and 1, the size of the formula is going to shrink significantly with high probability. In fact, it's going to shrink so much that there's going to be very few clauses of width greater than 1. So that's kind of the technical kind of lemma that underlies the proof. But yeah, once you show that, you get kind of the analysis, the result that they have. So how do we improve on this? So one issue here is the presence of k. So we want algorithms for k-sat we want algorithms for max-sat in general rather than max k-sat. They have an algorithm for max-sat in general by reducing to k equals log c, but there's an extra step, and we kind of do away with that. And in fact, somehow naturally, we shouldn't require to do that. We should be able to work directly with clauses rather than with CNFs as formulas, counting the literal size. So this is one issue, and also there's the dependence c squared. And the way we get around that is using kind of an approach which is quite traditional in branching algorithms, which is a measure and conquer approach. So essentially, what we do is we assign a measure to the formula, so a measure mu. And the measure for a formula is just going to be the sum over clauses in the formula of mu of c, where c is a clause. And the measure of a clause is only going to depend on the length of a clause, right? So the measure of a clause is going to be some sigma size c, and we're going to choose the sigma i's appropriately to kind of factor in a knowledge of what we can do for max-sat for various clause widths. So yeah, I mean, this is an approach that's used quite often in branching algorithms to somehow identify the right kind of parameter to make progress on. So measure is a way to identify the right parameter to make progress on. But quite often, this progress is measured in a local way. And I guess the difference here is that we measure this progress in a global way using these concentration results. But it's the same kind of idea. And basically, for this algorithm A here, we're going to set so mu1 is going to be 0 because for max 1 sat we can solve it in polynomial time, and then the mu's are going to increase after that, and then mu I is going to be equal to 2 for I greater than or equal to 2. So this is just kind of a branching algorithm where we're going to reduce everything to one CNF at the leaf. But we can do something different using the fact that max 2 sat is in time 2 to the omega n over 3, that we have savings there. So we don't have to have leaves that are 1 CNFs. We can have leaves that are 2 CNFs and then apply Williams' algorithm. And that would correspond to a different choice of measure. So that would correspond to mu1 equals 0 and mu2 as well equals 0, because we can do something non-trivial for max 2 CNFs, for 2 CNFs. And then we have mu3 equals 1, and mu4 equals 2, and mu I equals 3 for I, and so on. So this is kind of like a generic approach which given like some good algorithm for k-sat will give kind of an algorithm for max-sat in general with Cn clauses with non-trivial savings. So if you just kind of extend this kind of measure approach, we get these kinds of savings here. Yeah, so basically our algorithm is quite similar in spirit to the Sakai, Seto, Tamaki algorithm. It's slightly different, but the spirit is similar. We kind of optimize analysis a bit more, and we find a way of kind of reducing in general to k-sat. Okay. Any questions? Yeah, maybe I'll just mention one more thing, that this kind of like measure-based approach actually gives us something interesting from C and F sat as well. So we get, so this is not in the paper, but it can easily be shown using the techniques in the paper. There's a branching algorithm for C and F sat. With savings omega 1 over log C. So there are algorithms known for CNF sat with sayings omega 1 over log C, but these algorithms don't branch on variables. They have to branch on disjunctions or other functions of the variables. But somehow implicit in our approach is kind of a different way of reducing from CNF sat to bounded width CNF sat, which is based purely on branching on variables. And that can be used to get an algorithm which is a purely branching algorithm for CNF sat. And this kind of idea might maybe have some implications that are interesting in other contexts, such as sparsification, which remain to be explored. And I think another interesting question is just to limit, to kind of explore the limitations of branching for optimization. In some sense, branching should be much less powerful for optimization than for solving K-sat, exponentially less powerful in some sense. And maybe there's a way using proof complexity to formulate this and to show this. So that's on the problem. That's open. Thanks.
Thanks a lot. Are there any questions?
Yep.
So these savings for CNF sat that are implied by your algorithm, do they match the best savings for?
Yeah, they're the same. Yeah.
And if I remember correctly, they also have some savings for circuit satisfiability with certain density. Can you use the same?
Well, not for circuits in general. Do you mean bounded depth circuits?
I think bounded depths, yeah, with the density C and
yeah, that's right. Yeah, I mean, yeah, we could match that as well. Yeah, I mean, we've got to kind of use our kind of width reduction technique, and there's kind of a concentration result due to Hostad, a newer concentration result, which gives kind of the right parameters to apply this. So yeah, we could get that as well.
Any more questions? Maybe I can have one. So I was just wondering during the talk, are there any hypotheses or conjectures regarding the sizes of savings that you can get for different values of max-sat or CNF-sat, which would be something like threatening of strong ETH? So is it investigated?
It hasn't been investigated, but it's a natural thing to do. I mean, especially considering that something like the reduction from CNF sat to orthogonal vectors kind of preserves things exactly, right? So you could kind of look at more refined savings. Yeah, in which case you need even more fine-grained reductions to study this. But I think, well, it's not clear how many people even believe that omega n over k is the best savings you can get, or n over log c. So when belief in that is not very strong, maybe it's not clear whether to make that conjecture.
To confirm strong ETH before we get it.
Yeah, or actually our intuitions that we can't do better. We need to confirm, maybe study that longer before studying such things.
Yeah, okay, thanks. Yeah, so let's thanks again.